Good morning. In last class, we have seen about the static frictions. Now we will see one application of the friction and how the frictional force helps to maintain the system in equilibrium condition. The application of frictions are ladder friction, wedge friction, screw friction, and belt friction. Now we're going to see in detail about the ladder friction. Friction plays a crucial role in preventing a ladder from slipping when placed against a wall. The frictional force acts between the ladder and ground surface and also ladder and the wall. Just imagine that if you are keeping a wall in a very minimal keeping the ladder in the minimal inclinations, what will happen? If I'm keeping a ladder in this minimum inclination, I'm trying to climb. There might be a possible to slip. If we keep the ladder in inclination, we will not able to reach the destination or there might be slip. So the inclination also, inclined angle, the inclination of the ladder also matters in maintain the system in equilibrium condition. Just think of that. If the wall is very smooth, there is no any support in the wall. There might also be a chance to slip. If the floor is very smooth, then in that case also the ladder might slip. So all the conditions are very essential and very important to maintain the ladder in equilibrium conditions. So this is a major application in many areas. We'll see a problem, simple problem in the concept of friction. Before that, we'll just see the free body diagram of ladder. Here, the nature of the ladder while climbing, it will move in this direction, the direction of motion in this direction. Therefore, the frictional force should act in the opposite direction. This will be of frictional force. Yeah. So we know that in all the contact part, we have a reaction force that is perpendicular to the lying plane. This is normal reaction. Here also, the ladder will move in the downward direction. So the frictional force, F, is in the upward direction. F, frictional force. So the reaction, normal reaction force is perpendicular to the contact plane, that is lying plane. This is the contact portions. So therefore, the normal reaction will be perpendicular. The self weight of the ladder will act at the midpoint. The self weight of the ladder will act at the midpoint. We know that. And if any object or a man is climbing on a ladder, we have to calculate the weight of the man so that the ladder will be how the ladder will be positioned or the inclination or whether the ladder will start to move. These are all can be calculated based on the weight of the man who is climbing on the ladder. Let's get into the problem. A uniform ladder of 4-meter length rests against a vertical wall with which it makes an angle of 45 degrees. The coefficient of the friction between the ladder and the wall is 0.5. And that between the ladder and the floor is 0.5. A man whose weight is 1/2 of that of the ladder ascends it. How high will it be when the ladder slips? So, a diagram was given for this question. First, we have to understand the question. The ladder is of length of 4 meters. And it is leaning against the wall. The ladder length is of 4 meters and leaning against the wall. The inclination of the ladder is of 45 degrees. So the coefficient of friction between the ladder and the wall, this is the ladder and the wall, it is given as 0.5. And the ladder and the floor is given as 0.4. If a man whose weight is 1/2 that of the ladder, the weight of the man is 1/2 that of the ladder. That is, if we are assuming the ladder weight as W, then the weight of the man is 1 by 2 into W. So we have to identify if the man stands in one particular position, it starts impending. So till that, the ladder will be in the equilibrium conditions. We have to assume for that case, the ladder is in the equilibrium conditions. So we have to write the given data and then we have to draw the free body diagram. The frictional force in the upward direction, the reaction force in this side. Similarly, the friction force in right side and the reaction force is perpendicular to the ground plane. So let us take the x be the distance between the ground floor and to the man where the stands in the ladder. Let W be the weight of the ladder and R, F be the normal reaction to the flow. So therefore the weight of the man will be 1 by 2 into W, that is 0.5 into W. We know that the frictional force on the floor, F, frictional force is equal to mu into R. That is, mu is nothing but the coefficient of friction. The coefficient of friction between the land and the floor and the ladder is given as 0.5. So 0.5 into RF. The frictional force on the wall is 0.4 into RW. That is, FW is equal to mu W into RW. That is, mu W is nothing but coefficient of the friction with respect to wall and the ladder. 0.4 into R. So resolving the forces vertically, RF plus FW is equal to W plus 0.5 W. That is, RF plus FW is equal to 0.5 W. Now we have to resolve the forces horizontally. We'll get RW is equal to F. That is 0. F is the coefficient of friction into RF. RF is equal to 2 RW. Now we have to substitute the value of RF in the above equation. We'll get the equation as 2 RW plus 0.4 RW is equal to 1.5 W. We'll get the RW as 0.625 W. To find the values, we have to take the moment about a point A. So moment about point A is equal to W into 2 cos 45 plus 0.5 W into X cos 45. This W into 2 cos 45 and 0.5 W into X cos 45. These are the distance, weight into perpendicular distance. That is equal to RW into 4 sin 45 plus FW into 4 cos 45. By substituting the value of RW, we'll get the equation as W into R 2 cos 45 plus 0.5 W into X cos 45 is equal to 0.625 W into 4 sin 45 plus 0.25 W into 4 cos 45. Dividing W sin 45 on both the sides, we'll get the equation as 2 plus 0.5 X is equal to 2.5 plus 1. From this, we can get the value of X. X is equal to 3 meter. By substituting the X value, we can calculate the weight. Here, they are asking for the distance only, so we'll stop the problem. If we want to calculate the weight of the man, then we can substitute the X value in any one of the above equation, and we can get the value of W. Thank you.